So in our final section of chapter 3, we take a look at building functions, or mathematical modeling is another way to look at it. It's going to look like application problems or word problems to you. The key here is that we are writing functions. So we're not solving anything. We're not going to get a numerical answer at the end. We're writing functions. The one thing you have to remember is a function written in terms of x means that x is the only variable that can appear on the right-hand side. And that's the key to this whole section. So let's remember that as we work through our problems. We have 6 examples to look at. So example 1 reads, let P be a point on the graph of y equals x squared minus 5. We're going to first express the distance from P to the origin as a function of x. Okay, so you look at those words and say, I have no idea what's going on. So let's draw a picture more than anything else. We already know what the graph of y equals x squared minus 5 looks like, thanks to our toolbox or library of functions. So that's our friend, the parabola that's been shifted down. So we can draw that picture pretty easily. Something like that. So there's the graph of y equals x squared minus 5. And P is a point on this picture. And to make it look the best, we're just going to put it over here, but it really could be anywhere. So there's our point on that graph. What we want to do is find the distance between this point and the origin. So we need that distance. Okay, well, we know the distance formula. So a gentle reminder of the distance formula from clear back in chapter 2. The distance is equal to x2 minus x1 quantity squared plus y2 minus y1 quantity squared. So our distance is going to be, let's use this as our x2. So that would be the square root of x2, which is x, minus x1, which is just 0 squared, plus same thing in terms of the y's, y minus 0 squared. Well, cleaning that up, you're going to get the square root of x squared plus y squared. And no, you can't just drop the squares and square roots because that sign on the inside, this is not a true statement. So this is a true statement, but don't take it any further. Okay, so the difficulty is we want to write this as a function in terms of x, because that's what the directions are asking for. But we have a y, so we need to get rid of this. So we want to eliminate, get rid of somehow. So when you do the substitution here, and you'll see that as a common theme pretty much through all of the examples. So we already know that y is equal to x squared minus 5. And because we're on that parabola, we can use that as our y. So they're going to give us a mechanism to substitute in for that variable we do know. So we're going to do a straight substitution. Get the square root of x squared plus, now in place of the y, I'm going to plug in the entire x squared minus 5. And there's our function in terms of x, because x is the only variable on the right side. It does go on and ask us to evaluate it. What is d if x is equal to 0? So we're going to come in and replace all the x's with 0. So it would be d of 0. That's going to be equal to the square root. Well, that's 0 squared plus 0 squared minus 5 squared. So that's 0. That's 0. We're going to get 5 and squared. That's going to be the square root of 25, which is 5. Well, that was a nice numerical answer. And it should make sense why the answer is 5, because if x is 0, this is where we're at. We're at this point right here. And how far is this point from the origin? Well, it's 5 units from the origin. So that answer of 5 makes perfect sense in terms of the problem. So there's your first building of a function using the distance formula as a starting spot. I'm going to leave my reminder there for one more problem. In example 2, a slightly different type of problem. It says a right triangle has one vertex. The vertex is a corner. On the graph of y equals 16 minus x squared at x greater than 0 at some point x comma y. Another vertex at the origin, and the third on the positive x-axis at the point x comma 0. Express the area of the triangle as a function of x. Okay, so again, they gave me an equation to work with. 16 minus x squared. We're going to draw a picture because we have a triangle sitting inside this parabola. So here's our parabola. It is opening upside down and it's been shifted up 16. You could rewrite this as negative x squared plus 16 to make more sense for that transformation. So we've been moved up. We're up here at 16. And that looks something like that. So there's the 16 minus x squared. Now we've got a triangle. It's got one vertex on this graph, and it does tell me x is greater than 0, so it's a positive x value. So we're just going to label a point right here, x comma y, make that one corner of that triangle. It goes on to tell me that another vertex or corner is at the origin. So that's right here. And because it's a right triangle, it's either going to drop straight down or straight over. The directions tell me that the third corner is on the positive x-axis, so this is coming straight down. And there's the right angle sitting there, and there's our triangle. So what we're trying to do is find the area of this triangle. Yeah, it helps if we know what the formula for the area of any triangle is, and that is 1/2 the base times the height. So for my picture, this would be the base and this would be the height. They're always the perpendicular distance to each other. But we need to know what the base and height are in terms of our picture, not a B and an H. Sorry, there goes the marker again. Okay, so we need this distance right here. Well, if I'm at the point x comma y, then isn't this x and this is y? So isn't this distance x and this distance y? So in other words, if we're on this and this is the point 2 comma, I plug in 2 and it gives me like 12. If I plug 2 into that equation, then this distance would be 2 and this distance was 12. If I'm at the point 1 comma 15, then this distance is 1 and this distance is 15. So we don't know specifically where we're at. So we're going to pick up this and write it as a generic function. So we're now going to come in and replace our B and our H with our X and our Y. So the base of our triangle is X, the height of our triangle is Y, and we're writing that as a function of X. So here again, we have the same issue. A function in terms of X can only have X on that right-hand side, so we need to get rid of the Y. But again, we know what Y is equal to. Y is equal to either negative X squared plus 16 or 16 minus X squared. I'm going to go for their original formula. So that would be 1/2 X. Now replacing the Y with 16 minus X squared. I'm going to go ahead and clean it up. This is a simple cleanup. So I have half of 16, which is going to be 8 with the X, and half of that's going to give me a minus 1/2 X to the third. And there's the function. Now what you do with these in the next math class that you take after this one is you're going to take these guys, you're going to graph them and find the maximum area or the minimum area that you can squeeze inside of this parabola. So this is just the starting point to another problem later on.